Dr. Jain's area of interest include signal and image processing, time frequency analysis, and wearable healthcare technology and algorithm development aimed at improving patient diagnosis, assessment, and remote healthcare. His work has been published in peer-reviewed SCI index international journals and reputed conferences. Furthermore, he has contributed as a reviewer for several esteemed international journals and conferences. So, with this, I would like to hand over the session to Dr. Puneet. Welcome over to you, sir.
Thank you for generous introduction. Okay, so first let me share my screen and let me confirm that is it visible. I hope
Yes, sir.
my
Yes, sir.
screen is visible now.
Yes,
Okay,
sir. It is
just
visible,
let
sir.
me just let me check that if I change the slide, is the slide get changed?
Yes, sir. It is getting changed.
Okay,
Mhm.
fine. Thanks.
Okay.
So should we start?
Yes, sure, sir. Sir.
Okay. What is the expected time? I think I should close by 6. Okay, so 15 minutes approx, right? 40 to 15 minutes.
Yes, sir.
Okay, fine. I start, I hope the basic of the deep learning or the CNN model has been covered in some of the talk.
Yes, yes,
Is the basic of the CNN has been covered?
yes, sir. It's been covered.
Okay, okay, fine, perfect. So here in this presentation, I am going to talk about MRI scans specifically for stroke lesion detection, and we are going to discuss the deep learning methods for this particular task. And in the deep learning also specifically we'll discuss about one particular architecture called UNet. So here we are going to focus on these three components. First we'll discuss little bit about the CNN models and the popular CNN models. Then directly we'll jump to the main topic of this talk, where we'll discuss about the application of UNet model for brain image analysis and specifically the stroke lesion segmentation. I have also included one more topic in this talk to describe that how we can use UNet for various different biomedical applications. So in this another application I'm going to discuss about denoising application of the UNet model. So let us start with the role of AI in healthcare. I hope now with this tremendous FDP conducted by Dr. Deepak, you have encountered a lot of applications of deep learning in healthcare. These are the glimpses that the classification of Alzheimer diseases, where we use the MRI scans to detect the Alzheimer or to detect the pattern of the Alzheimer disease. Then this is another interesting application where we put lots of electrodes on the abdominal of the maternal to analyze the fetus movement, and any kind of normal or abnormal pattern can be detected through these electrical activities of the fetus. Then this is another application which was very prominent during the COVID to analyze the pneumonia symptoms using the chest X-ray images. Then a very popular method to analyze the cardiac activity using the electrocardiogram. So in various applications, sometimes we use the images of the ECGs, sometimes we use the signals of the ECGs, 3 leads, 12 leads, etc. Then this is another application where we use the mammogram images of the breast to detect the cancer or to prognosis of any cancer related issues. Then this is also an interesting application where we analyze the bone structure of a wrist and the hand fingers to analyze the age assessment as well as any abnormality with the development of the bones. So this is just a glimpse of how the deep learning models have been found the applications in the medical domain. There are n number of applications where people are using various kind of deep learning models for various purposes. So let me just give you a glimpse of how the CNN model journey started. So I hope everyone is familiar now that in the when we talk about the deep learning model, so CNN, which is one of the deep learning model, consists of the two major components. One is the feature extraction or learning, and the second one is the classification. And that's how the deep learning models are distinguished through the conventional machine learning techniques. That in case of conventional machine learning techniques, we have to do the feature engineering. That means we have to identify manually or through the engineer what kind of features would be beneficial to perform that particular task. For example, if I have to detect the faces of a human, then I have to identify what kind of features would be prominent, would be distinguished features which will be able to detect a human face. Now, in case of deep learning, in general, what we consider is that the task of extraction of feature is also provided by the model itself. Although, in case of for that particular purpose, there is a specific part in deep learning model. In case of CNN, these are the convolution layers. So there are two specific tasks of these convolution layers. One is the automatic feature extraction. I am saying automatic because what happens is that in these convolution layers, as you might have encountered in the previous talks, these convolution layers are incorporated with various convolution filters, and filters are nothing but just a set of matrices, right? These matrices get convolved with the input images and they try to extract some meaningful information. Now, in case of handcrafted features, that means in the manual process, we have to identify which kind of filter we have to use. In case of CNN, the values of these filter will be learned by during the backpropagation algo or during the training time, right? So that's how which kind of feature has to be extracted will be identified during the training time. And that's how we call this that, okay, this feature engineering task is an automatic task compared to the manual task in conventional machine learning technique. There is another important aspect of these convolution layers, which is followed by another operation called max pooling. So the point is, before reaching to the classification stage, we want to reduce the number of features, because as the number of features increases, the densely connected layers will explode the number of learnable parameters. So just to constrain the number of learnable parameters, we would like to reduce the number of features. So these are the two important tasks of the convolution layers, to extract the features automatically, plus the reduction in the size of the features. And after that, we can use any conventional machine learning technique to perform the classification, whether it is a fully connected neural network, or in fact, we may use any machine learning technique like SVM, decision trees, or any other technique, right? So that's how the journey started of the convolutional neural network through LeNet 5, proposed by LeCun in 1998. Although I would like to emphasize that it's not like people were not using the CNN concept before this particular point. But the point is, these are certain milestones where these models produces some significant results in a particular application, and they become popular, right? And that's how we know that, okay, the LeNet came into 1998, right? So that's how the journey started. After that, the major breakthrough appears in 2012, where the CNN based model get to win a very popular challenge called ImageNet, a large scale image classification challenge. uh, so even it the challenge was appeared in 2010, but the first two winners in the year 2010 and 11 were cello networks. In 2012, the first CNN based model was the winner, right? And these, if you are able to observe these numbers are the error rate, right? So if there are 100 images, this model was giving correct output for approximately 83.6 images, right? Now, after that, all these winners are based on the deep learning models only. So after 2012 success, everyone was focusing on the deep learning models, right? And that's how you can observe that as the number of layers increases, the architecture of these models increases. I will just give the glimpse that how the people change the architecture of these models. But then after that, researchers try to optimize these models so that the performance can be improved further. So you can observe by 2015, the error rate becomes 3.6. Even in 2016-17, it further reduces. But 2015 was an important breakthrough because by 2015, the deep learning model for this particular task beat the human performance. So another group conducted the same experiment with the human, and the error rate was close to 5.1. Right. That means if the model is producing lower rate compared to the human performance, that means the model beat the human performance. Right. So after that, again means people started exploring various attention mechanisms to incorporate in the CNN model, etc., to improve the performance of these models. So I'm just giving a glimpse that how people were trying to improve the accuracies of these different models. I'm not going into much detail about these architectures and why these architectures look like in this way. This is first one, the 2012, the winner of the ImageNet challenge, AlexNet. So here there are 8 layers, 5 convolution layers, and the three fully dense connector layers, or we call them dense layers. In case of ZFnet, it is also similar to the LXNet, a sequential pair of the convolution and max pooling, and at the end there are 3 dense layers. Although the combination of the size of the filters and the number of filters were varied. In 2014, an interesting model came into the picture called proposed through the Google's team, and that's why it is also termed as Google Net. Otherwise, it is also very popularly known as Inception Net. The reason behind the name is that there is a model in the model. In many layers, there is a model itself. That means if you would be able to observe on this highlighted part, just let me use the pointer option. Okay. So if you would be able to observe this particular part, you will see that there are multiple convolution layers in each layer. And that's why this model was termed as inception layer, right? Of course, there are certain rationales, and in another part is that empirical, right? So these models were produced based on the two things. One is the rationales, or the people who are trying to understand that what are the factors where the model is lacking to understand a particular problem. And second thing, of course, empirically, that means we have to do certain experiments with the different hyperparameters, and we have to come up with the hyperparameters which is producing the best result for that particular task. Similarly, the VGC16 came into the picture where again the sequence of the convolution and max pooling layers were changed, and very means very interesting. One cross one convolution layer was introduced here. You in this case, max pooling was not attached with each convolution layer. In fact, multiple convolution layers were followed by just one max pooling. Of course, means everyone have their own decision, and every audience should argue that why this model look like in this way. The point is, of course, that's the beauty of these deep learning models, that you should experiment, you should try whatever comes into your mind, right? And everything is fine if the two curves looks good. One is the validation curve, and one is the training curve and the validation curve. If both are reducing continuously, and the gap is negligible, in that case we can say, okay, my model is not either in underfitting scenario or an overfitting scenario. Every model you can argue that okay, this architecture produces these kind of results. After that, a very interesting model came into the picture called ResNet. So the one issue was observed that as the number of layers increases, the gradient does not reach to the initial layers. So to resolve that, in the ResNet, skip connections were created. So skip connection is nothing but, if you would be able to observe here, some direct connections from the forward layers to the further layers, downward layers were created, so that the when the backward propagation will be calculated, the gradient will reach directly from this link to the upper layers, right? And that's how some up to a certain extent the vanishing gradient issue was resolved, and that's why the ResNet produces very good results. And in fact, in many recent applications, we use the ResNet models in one or another way. After the success of all these models, probably by 2015, okay, so there were two major reasons why people's means that research community explored the use of deep learning models. One is that their prominent results for the image classification. Second thing is that by 14 and 15, uh, various research groups created a large data set or large amount of data set for different applications like the segmentation, for the time series application, etc. Because without the absence of a large amount of data set, deep learning models were not producing significant results, right? So by the point of 14 or 15, lots of applications and lots of architecture of the model came into the pictures. In addition to the CNN, like for the time series application, LSTM, RNN came into the picture. For like generative adversarial networks, radial basis functions, etc. So again, this is just a glimpse of different kind of architectures of the deep learning models came into the picture. So now let me discuss about one specific architecture of the deep learning model or the CNN model, that is called UNet, for brain image analysis, and particularly for the segmentation task. As I mentioned, I'm going to discuss, or in fact, I will say that I'm going to give a glimpse of how we can use the UNet model for the segmentation task and for the denoising task. So, when we have to perform the semantic segmentation, our objective is that we have to label each pixel with different color. So the overall we have to segment each region or each object available in the image. So that is called semantic segmentation. Semantic segmentation is nothing but assigning each pixel a class label. I hope by this particular example, you would be able to understand what we mean by the semantic segmentation. So that is our task in case of brain MRI images. Before the unit, peoples were trying to perform these kind of segmentation and other tasks through the CNN architecture called autoencoder, where the size of the input and the output is same. So here, what is the there are we can consider that in this model there are two parts. One is the encoder part, and then there is a decoder part. The encoder part converts the input into a latent space where you can say we are representing the input features into the sparse representation, and then we are using these sparse representation to extract the meaningful features. So in fact, we can use it for the denoising. We can use, once the model is get trained, we can use the one part for the compressor and the second part for the decompressor type. Another application, as we are going to discuss, is the segmentation, etc. So this particular architecture becomes interesting. However, there were lots of issues. Issue is that as the number of layers increases, again the vanishing gradient issue becomes so prominent that this specifically autoencoders were not producing significant results in many applications. So people started working on various to resolve various issues in these models. Another important model for the segmentation task came into the picture called FCN, fully convolution neural network for the semantic segmentation. After these attempts, in 2015, Ron Berger came with an architecture called UNet, and I hope you would be able to observe that why the name of the model is U, because the shape of the model was constructed in a U shape, right? If you will if you will ignore these gray lines, you will consider that this is nothing but a sequential network, right? Where the left part is the encoder part. Let me go to the next layer. Yeah. So there are two phases in this model. One is the contraction phase, where we are reducing the size of the input feature map, and the second is the expansion phase. Similarly to the autoencoders, right? There was then contraction phase followed by the expansion phase, where we were calling encoder and decoder. The addition thing is that here we are having these gray lines, which are called the skip connection, and they played a very interesting role, similar to the ResNet, right? They provide a direct connection from each encoder layer to the decoder layer so that the information get passed directly from the top layers. Similarly, through the backward propagation, they help to reduce the vanishing gradient issue. And that's how the UNet model produces significant results in many applications, right? And that's why we are going to discuss two applications of the UNet further. So as I have mentioned, these are the skip connections. The output of each encoder layer is passed, or you can say the bypass to the decoder layer. You should be able to observe that we are providing some input, our input, either it might be a 1D data or 2D data, and then we are going to generate the same size of output corresponding to the input. The number of convolution layers at each encoder that depends on the particular application, right? You again, this is kind of, you can consider a hyperparameter, and you can play with these hyperparameters, that how many convolution layers you have to put on in each encoder or decoder layer, what should be the size of the filters, etc. This typical architecture shown in this particular slide is probably from the paper produced by the Ron Berger. And in fact, the Ron Berger produced this UNet model first time for the biomedical application only. So here, this is the example where the Ron Berger used the UNet model for cell ISBI cell tracking challenge 2015. You can observe that this is the input image and how beautifully the UNet model is segmenting the image. So let us discuss about the brain MRI image now. I hope. Uh, okay, so let me just discuss a little bit about the brain stroke and then how we get the intrinsic information about the brain analysis. So brain stroke is a cerebral vascular disease where the cerebral nerves get blocked, and due to that, the blood supply to the brain get interrupted. The burden of the brain stroke can be analyzed by the fact that this is the second leading cause of death, which is responsible for approximately 11% of total deaths worldwide. That's why it is important to diagnose the stroke lesions, or if there is any cerebral blocks at an early stage, so that a proper treatment can be initiated. You can observe that in this right image, this is an MRI scan of a normal brain, while the right part of this image is showing a MRI scan of abnormal brain, where the lesion part is clearly visible, right? Although means it depends which kind of sequence and which kind of which axis we are analyzing. I will discuss a little bit later about these terminologies. Yeah. So now we have different modalities, imaging modalities to analyze the internal structure of the brain. The most prominent one is the MRI, that stands for magnetic resonance imaging. Then there are other techniques. I think the previous talk was focusing on the computer tomography or the CT images. Then there are two other more techniques like MRA, magnetic resonance angiography, and computer tomography angiography. Magnetic resonance imaging is based on the magnetic resonance concept, and it is very sensitive to changes in the soft tissues, and that's why it provides ample diagnostic features at an early stage if there would be any change in the soft tissues in the brain or any part of the human body. These MRI scans can be analyzed in three different planes. Either it might be horizontal plane, medically termed as axial section, or coronal section, or sagittal section. Although we can create a 3D object of multiple slices, and these slices can be viewed from any particular angle, framing these three sections. Another thing, in case of MRI, based on the the, the specification of the machine, that is it capable to capture the 1 Tesla, 1.5 Tesla, or 3 Tesla machines. We can create the T1. We can create different imagings. Then there are different steps when we resonate the protons of the hydrogen atoms. So okay, okay. Let me. I will come back to this slide again. So this is just an layout of the MRI scan machine, where we means this circular shape consists of the magnetic resonance field creation instruments, and then we pass on the particular organ to which we want to scan. What happen is that okay, this is just one slide where it is described that how many researchers got the Nobel Prize for the contribution in this particular field. So by just observing these number of Nobel Prizes for this particular field, we can understand that how prominent this particular innovation is in the medical application specifically. Yeah, so here I have just incorporated few slides to describe that how we get the MRI scans. So the point is, our body, or in fact every material, is consists of the atoms, right? So there are lots of atoms in our body, and there are different types of atoms. We are interested in specifically in the hydrogen atom, because first of all, the presence of hydrogen atom is in every cell, either in the combination with the hydrogen in terms of the water, or in terms of the different material through the combination of the carbons. Is Specifically in the hydrogen, there is only one proton, right? And we want to observe the spinning mechanism of this proton. So it would be easy to measure the spinning mechanism of this proton, and that's why we are interested to measure the presence of the hydrogen and the characteristics of this particular proton available in the hydrogen. Now the point is, in our body, different cells at different organs are composed of different density of the water and other molecules, right? So in the water, as we know that there are two hydrogen atoms and one oxygen atom. That means now, if in any particular organ, and let us talk about with the brain, because we want to analyze the brain strokes. If there would be any abnormality, the ratio of the water and other molecules will change. And if that will change, the number of atoms in the water, means the number of hydrogen combined with the oxygen, and the number of hydrogen atoms combined with the COH or other molecules will change. Now, due to the different density, the energy spectrum of these hydrogen protons specifically are different, right? The bonding, what they call, the bonding energy is different into these different modules. So if the density of these molecules will change, their characteristics, when we excite these protons and we relax these protons, the characteristics of these molecules will change based on the density, right? And that's why if the density will change due to any abnormality in any particular organ, that would be able to observe through the magnetic resonance effect, right? So that's how when we excite and relax these protons, there are different phases, and these phases are termed as the T1 weighted, T2 weighted. Then we have diffusion weighted imaging, and then the different imaging techniques came into the picture, right? So it depends on which particular stage we are on the stroke. We have to identify which particular imaging modality will be helpful, which image sequence will be helpful to diagnose particular disease. Like in this case, DWI and FLAIR are describing that there is some signature of the abnormality. So if the mask is nothing but the ground truth, which is describing that this is the actual presence of the abnormal tissues. While in case of T1W, T2W, this abnormality is slightly reduced, means not prominently present. So that's how means different methods have used these different modalities in different ways. Some of them have only used one of these modalities. Some of them have used the multiple modalities to perform the same task. Okay. So now this is a summary of the data sets available for this particular task. Prominently, these are the two recent data sets. One is the ISLES. Okay, where is it? Yeah. One is the ISLES presented in 2022. That means it's a recently presented data set in the Mikai challenge. And there is another data set, which one is the Atlas. The point is, in these two data sets, the stage of the disease is different. Also, the sequence covered in these two data sets are different. In case of ISLES, the DWI, ADC, and FLAIR are used, while in case of Atlas, the T1 weighted images are there. The number of training and testing images are described here. So now, in the stroke lesion segmentation, this slide is describing that what is the specific challenge to perform the stroke lesion. So specifically, we can categorize these challenges in three broad categories. One is the intra-class inconsistency. That means the lesions, sometimes the lesions lesion part looks like a normal part. If you would be able to observe the slide 3, this is the lesion part. While if you will observe in case of the scan, the lesion part is not clearly visible. So this is an intra-class inconsistency. Interclass indistinction, sometimes it what happens is that, like in this case, if you will observe in the slice 2, this part seems that there is some lesion part, but actually there is, oh, okay, I think there is a lesion, right? Yeah, there is a lesion. In the slice 1, again, you can see that this part looks like that this is a lesion part, but in this is not a lesion. So this is one challenge: intra-class inconsistency and inter-class indistinction. Second, class imbalance problem. That means the number of lesion pixels are very small compared to the healthy pixels. Then another challenge is the fuzzy boundary for lesions. You can observe that one thing is that the boundaries are very irregular, and the number of uh, locations and the distribution of locations is irregular, right? So these are the challenges to perform the stroke lesion segmentation. This is again a typical architecture of the unit where in our research, what we are trying to do is that we are trying to incorporate some attention mechanism, either in the encoder side or in the decoder side, or some researchers. In fact, in some of our attempts, we can incorporate the attention mechanism in the skip connection, right? So uh, means in what how we are going to use this unit model is that we are going to provide the input MRI scan, and we are expecting a segmented part of the lesion that is an expected out of the unit model. This is another attempt of the unit model, unit architecture, where, as I mentioned, the people's research communities or researchers are trying to incorporate the attention mechanism. What happens is that in case of CNN, they extract the features automatically, as I mentioned, but uh, they lacks in the extraction of the global information, right? So that's how the people are trying to incorporate the attention mechanism, the channel attention mechanism, special attention mechanism, then the cross channel width, cross channel height attention mechanism, uh, self attention mechanism, global self attention mechanism, etc. So means that is a one particular branch of the study, that how the attention can be incorporated and can be improved to extract the global features more meaningfully, right? And this is just one of the glimpse that how the attention mechanism can be incorporated, right? In our work, we are trying to incorporate and come up with the new attention mechanism. So I have just included a glimpse of the results of various popular deep learning models in this particular domain. These are like unit, attention unit, deep play V3, race unit plus plus. So the point is now people are working on multiple aspects to improve the performance of these models for the stroke legend segmentation. One of them is the architecture of the unit model. So you can consider that some of them are incorporating the residual kind of convolutions in the encoder decoder. Some of them are trying to incorporate deep supervision kind of concepts where they are trying to incorporate multi loss function criterias. Then other aspect is to incorporate different kind of attention mechanism. Another aspect is to incorporate to update the loss functions. One another important aspect is to work on the pre-processing task, etc. And of course, means as I mentioned that one of the major challenge is the class imbalance. So people are also trying working on the augmentation technique to resolve the issue of a class imbalance, means at the event level as well as the pixel level. So now means I have specifically removed the result of the proposed our proposed method because that work is still under review. Uh, Through these results, you can observe that, in fact, these models needs the improvisation. Still, these unit-based models are able to detect the lesions with certain satisfactory results, right? Specifically, if you observed in out of these methods, existing methods, this PAMSNet is producing satisfactory results, right? In terms of the quantitative, these are the important matrices we use to analyze the performance of the models for the stroke legend segmentation, namely the number of learnable parameters and the number of flops to analyze the time and space complexity of the model. And then the die score, intersection over union, precision, recall, and host drop distance matrices. These are the matrices, quantitative matrices to analyze the result of the segmentation task. Right. I'm not interested too much on commenting on these results because, as I mentioned, I have deliberately removed the results of our proposed method. So, uh, in fact, in this case, you should be able to observe that the number of parameters reaches more than 8 million, or means the basic unit model is close to 8 million and most of other models are greater than this one, right? That means the size of the model becomes a little bit in the complicated side. Then we are also trying to incorporate various attention mechanisms. This is again a comparison of the various popular attention mechanisms. If you have heard about the self attention mechanism, squeeze excitation mechanism, then the CBAM module, the triplet module, then global self attention block module, etc. Okay, okay, 5 minutes. Yeah. So let us discuss a little bit about another application of the unit. So I incorporated this particular application to give a glimpse at how we can use the unit model for other application as well. So here I'm going to discuss about the denoising application of the unit, specifically for the heart sound signals. As every one of us aware about that the heart is a very important organ of our body. Means there are around 37.2 trillion cells in the human body, and the heart provides replenish oxygen to each cell. Right. That's why the heart functionality should be is very critical for the human body. Now, to analyze the functionality of the heart, there are different modalities. Many of are all of you like electrocardiography, phonocardiography. Of course, everyone one must have gone through the screening through the phonocardiography, where the stethoscope is used to analyze to audible to listen the heart signals. Then the seismocardiography, photoplethysmography, which is again a very popular technique, uh, and then echocardiography to analyze the internal structure of the heart. So let us specifically discuss about the denoising of heart sound signals. There are various regions due to which the heart sound signals may get corrupt due to the internal noise as well as the external noise, and that's why before performing the analysis of the heart sound signals, we would like to perform the denoising of these signals. And here I'm just describing the heart sound signal because that is one of my research work. We can use these models for any kind of applications which are related to either segmentation or denoising. So here what we are doing, this is one specific work we have produced where what we are doing instead of using the time domain, what we are doing, we are decomposing the time domain signal in the time frequency domain signal using the DWT, that stands for discrete wavelet transform. So here we are decomposing the signal into different detailed level coefficients and approximation level coefficients. We are applying the unit model. We are applying the unit model at each these different levels separately to perform the denoising. That means the size, whatever the size of the input coefficients, we are going to produce the same size of the coefficients at the output level, but the output would be denoised output, right? So the model will be trained for the noisy part with corresponding to the denoised part or the clean part. And after these denoise coefficient get obtained, the reconstruction phase can be applied to produce the denoise signal. So if any one of you are aware, in case of DWT based denoising method, what we do is that after decomposition, we apply the thresholding. And thresholding is a bottleneck of DWT based denoising method because if the thresholding value is little bit higher, they will suppress the diagnostically important features. But if the threshold is low, the noise will not be suppressed significantly. And that's how here we are not applying the thresholding. We are adaptively processing these coefficients using the unit model, right? And this is just a glimpse of the kind of idea, the kind of results we are getting. Specifically, if you will observe this third case, uh, in the middle part, you will observe that using the unit model, using the DWT unit model, uh, we are getting the result. So this is the clean signal. This is the contaminated signal through the synthetic noise, and we obtain this signal from this signal, right? That means from this noisy signal we got this denoise signal, right? All other methods get failed to reconstruct the murmur sounds, which is very important to perform the diagnosis, right? I have not commented much on this importance of these signals and other etc. So just leave that part. But the point is we want to reconstruct our original signal as close as possible, right? While suppressing the noise. And you can observe that these unit-based architectures are very effective to perform these kind of applications, right? Okay. So I have just listed down few papers, those who are interested to work in the heart sound signal domain. So these are few papers from where you can start on. Then the popular data sets, I have mentioned the data sets for the stroke lesion segmentation in the middle of the slides, while these are the popular data sets available for heart sound signals in the public domain. Out of these, prominently the researchers are using the dataset 1 and the dataset 3, right? Because the number of samples are adequate in these two datasets. So that's it. By this, I would like to conclude my slides. We have discussed about the unit and its architecture and its performance for the two tasks, denoising and the segmentation. We have discussed that how the encoder decoder structure and the SIP connections helps to extract the features efficiently to perform different applications. Uh, by leveraging unit, we can enhance the accuracy and reliability of automated biomedical signal analysis, ultimately improving diagnostic capabilities and patient care. In the future, as I have already mentioned during the slides, that how the researchers are trying to improve the performance of these models. One thing is that they are working on the architecture of the unit, like there is one specific architecture called the WNet, where there are two layers of the unit, etc. Then the people are trying to incorporate various and attention mechanisms in these models, and then means like other techniques like the domain adaptation techniques can be combined. The gain model can be used to perform the augmentation, etc. These are the team members in my lab. There are five PhD scholars and a few MTech students, in addition to the BTech students. By this, I open up the platform to ask the queries. Hello.
Yeah, participants. Okay, thank you. Thank you, Professor Puneet, for sharing your expertise with us. Uh, I hope participants have enjoyed your sessions. So now, participants, if you are having any queries, you can write in the chat box. So Professor Puneet will be happy to take your question. So I think there's a question in the chat box. So they cannot unmute their mic and talk to us directly. So they can only write the
Okay.
queries in the chat box.
Okay, fine.
I
So
think
I
there
think
is
there is one question. Can you please suggest a few of the lesser explored topics in terms of models or findings? Says like there is Windows of unit and its variation already available in research literature of medical segmentation. Yeah, it's a good point that means of course it's unit model has been explored for various applications, and as I mentioned, people are now trying to uh, explore various other architectures or way to uh, I will say that it's not like that different architecture, but people are trying to modify the architecture of the unit model so that wherever the unit model is lacking to extract the features, means so okay, different architectures. Okay, yeah, there are certain architectures for the in addition to the unit for the segmentation task, but specifically still most of the research groups are focusing on the unit architecture, considering their performance for segmentation task, right? As of my knowledge, unit is still as a prominent model for the segmentation task. For the denoising, this is just one application. Means I'm not able to observe much application of the unit till now. But as we are getting the prominent results through the denoising, I hope people will start to work on using the unit for the denoising in various other applications as well. Any other doubt?
yeah. So we can wait, sir, for 1 minute. Maybe they are typing.
Okay, no issue. Okay, I think Dr. Deepak, in any case, I will share my mail ID to the audience, and I will share these slides with you so you may share this with the audience. And at any moment, if they want to discuss any topic discussed in the slides, they can contact me through the mail also.
Yeah, I think that would be a good idea. But there is one more question, sir, by Pooja Soni. You
Yeah.
can check.
Yeah, sir. What approach was used to pass on the output of one of the encoder block directly to the decoder block? Uh, means I did not get the exact question, but are you asking about the skip connection? So in that case, it's means there is no tricky part here. That means what we are doing. If I will go to that slide,
Pass on the output of encoder block.
yeah.
Okay.
Yeah. So the point means here what we are doing here is that in means not we in case of unit model, what happen is that whatever the output of this convolution layer at this encoder layer 1, I am considering the encoder layer 1 first. So whatever the output of the last convolution layer here, that will be pass on. That means pass on means we are going to concatenate. Here there would be a concatenation, right? There would be a concatenation of the output of the encoder layer and the output of the previous decoder layer, right? So let us say the output of this was H cross W cross C, and the output of the previous decoder layer was H cross W cross C. So we are going to concatenate them. It will frame as H cross W cross 2C, right? Is it okay, or was the question, is the question different? Just like the ResNet, are the skip connections are used in the unit? Yes, means not in typically in the unit. Yeah, means your point is good. Means you want to correlate these skip connections as the skip connection in the ResNet. I will not say in that way, because in the ResNet what happen is that the skip connections are the sequential, while here the skip connections are the layered wise, right? That means the skip connection from the encoder layer 1 is passing to the encoder layer, decoder layer at that particular level only, right? Um, this is one thing. Means of course that's a good point that you relate these skip connections with the skip connection of the ResNet, because the purpose is same, right? However, I would like to comment one more thing is that what researchers are trying to do, instead of this ResNet block or the convolution block at this encoder layer, we can use the ResNet block, right? That means one particular ResNet block of ResNet model can be used as an encoder layer. Similarly, we can use the ResNet block at each level at the encoder as well as the decoder, and that is called the res unet. If you have observed in the comparison table, there are lots of variations of the res unit, right? Res unit plus plus, etc. So means of course you can correlate it in the rest. The skip connections can be correlated, but not exactly, because in case in UNet these are the layer wise skip connections, while in case of ResNet they are sequential. And second point is that we can use the ResNet blocks as an encoder or decoder convolution modules here. Any other question?
No, sir, I don't think other questions. So thank you so much, sir, once again for sharing your expertise or insights on unit-based segmentations. And you have also explained about
Thank you, Doc.
brief summary about the CNN architectures and the new connections that has been introduced over the years. Yeah, thank you so much,
Yeah,
sir. I think
well,
the participants have enjoyed your session and got a lot of information. Thank you, sir.
welcome, Dr. Deepak, and thanks for giving this opportunity to interact with the audience of this nice framed FDP. And as I mentioned, I will share these slides with you, and you may share it with the audience.
Yes, absolutely.
Yeah. Thank you.
Yeah, thank you so much, sir.
Okay. So I'm leaving the event now. Okay.
Yes, sir, you can.
Okay. Bye.
Yeah, bye. Participants, thank you so much for attending the session. We'll be having a validatory session followed by quiz test. We'll discuss all these things. I mean, maybe about how to share the slides I have all collected or from almost all the speakers, right? That was my job to collect actually all the slides and all. So there are links for the codes, the practical session. There are a couple of slides still pending from the speaker side. So I will discuss all about all these things, right? Just after 10 minutes, so we will start the validatory session around 6:15. So I request all of you to please join and share your feedback, which is very important for us. Right? If you're having any query regarding collaborations and many other things, you can also discuss with us. So we'll give you, the access. Basically the presentation access where you can speak to us. Then only you need to raise your hand here so that I will ask my staff to give you presentation access, and you can just talk to us directly. So kindly wait for 10 minutes. So we'll start the session. Thank you so much.